All right, let's get started today. I'm going to talk a little bit more about matrices and indexing into matrices and accessing columns and rows and stuff like that. And then I want to use matrices to do kind of like a little, our project for the day today is going to be to take a flow field that is take information about points in space and about how particles at those different points in space would move, and we're going to try to plot that flow field. So we're going to make a plot of how things would move in a plane. This is something that we'll be using later in dynamics, and so it seems like a nice idea to try and illustrate that. But first, we're going to start with matrices, and you guys have already used some of them. So for example, we did something like this, where we said, oh, let's build an object that has 2 rows and 3 columns, and those are the different shelves. And I hope you guys will remember how to access them. You indicate before the comma which row it is, and then you indicate after the comma which column it is, and that gives you access to that particular shelf. And say we can, if we put something in the second row, second column, then when we ask what y is in the second row, second column, we've got that number. And just as with vectors, you can access more than one element. With matrices, you can access more than one row or column. So for example, you guys will remember that, say, we could make a vector that was something like this. And we could access, say, from the first to the last. Let me make a slightly longer vector. Let me call it 1, 2, 3, 4. And we could access from the second to the last by doing something like this. And it's exactly the same notation that now we're going to use with matrices, except that instead of just specifying position within a list, we need to specify, are we talking about the rows? Are we talking about the columns? So say here, the vector 2 to n started from the second element and went all the way to the end. So let's make a matrix. And this time, instead of using zeros, I'm going to write it out by hand. Okay. And when you're using matrices, I want to point out again, when we did vectors, if we wanted something that was a one-dimensional list, we separated things by commas. Now there's going to be 2 different symbols that we're going to use to separate things either by rows or by columns. A space means next column, and a semicolon means next row. So for example, if I write this, that would mean I want something that has 3 columns. And since I didn't use the commas, this is not going to be a one-dimensional vector kind of item. It is actually a matrix in the sense that it has both rows and columns. This particular one has only 1 row. Okay. So we could separate our columns with spaces, and we separate our rows with a semicolon. So if we write this, what we get is this object where the first row is what we defined before the semicolon, and then the next row. So now here we've got, let's make a matrix with even more. Let's make it with a total of 12 elements. And I put too many square brackets. Okay, so here's our 3 by 4 matrix. And now let's say that we want to access the second through the last column. So with matrices, always goes row first, and then the column. So if we want to access the second through last column, we'd write something that could look like this. In terms of which rows we want, we're just going to write colon. That means give me everything. In the same way as when we had a vector, if we wrote vector of colon like that, that said give me everything. Right? That's all the way from 1 through 4. It's going to be the same with the matrix. And here we're saying give me all your rows. But now give me the second through the last column, right? Because the comma is what's separating, are we talking about the rows, or are we talking about the columns? So this should look like something that has all the rows, but only columns 2, 3, and 4. So it should look like this part of the matrix, right? So let's see what we get. maybe. I guess I haven't done this particular thing in Julia since I restarted it, so it was a little slow the first time. And here is that part of the matrix. So, for example, suppose that we wanted the second through the last row, but all columns. What would I write here?
2, and comma, 4.
Exactly, right? So this would mean we're before the comma, so we're specifying the rows. We want from the second to the last one. After the comma, we specify the columns. We said all of them. And we can even combine. For example, we could say we want the second through the last row and only the third column. Okay, let me show you M again. So this was the original M. If we ask the second through the last row, that's these two rows. And if we ask only for the third column, as we did over here, then that's these two elements. And so it's exactly the same notation as you use with vectors, but the thing to remember is now you're specifying both the rows and the columns, so you have to tell Julia what you want for the rows and what you want for the columns. And you can set values like this too. So for example, if we say that, that means we'd like the second through the last row in the third column, we'd like all of those to be set to 1,000. So now when we ask what M is, when we ask what M is, here's the original M, and now we've set the second through the last row, third column, we've set it to 1,000. And we can set a whole row as well. So let's say that we had our original M again. Okay. So I've just redefined M to be back this matrix. And let's say that I want to set the second row. So there I'm telling Julia I want the second row, I want all elements of the second row. I could set it to a scalar value, for example, like I did with 1,000, and then all of the elements in the second row will acquire a particular value. Or I could say, you know what, I want to set each of the elements to a different value. And so this is now specifying something. So for M, we had 3 by 4. And so now here I'm specifying the second row, all of the columns. So this is a 1 by 4 vector. So if I don't want to use the shorthand of setting it to a scalar and saying set all of these 4 elements to a single value, to the same value, then if I want to specify each one, I need to specify 4 different values. I need to say what goes in here, what goes in here, what goes in here, and what goes in here. So, for example, we could say 1,000, 2,000, 3,000, 4,000. Let's see if that works. And now we've set M like that. Yes?
If you set a vector of less dimensions than sorry, if you set a vector that's shorter than the length of the thing you're trying to do, does it give an error, or will it like try and...
So for example, let's say that now we had said, let's just do this. Okay. So in this case, Julia doesn't know. You're telling me 2 elements. On the left-hand side, you specified something that has 4 shells. And you're telling me 2 things. So Julia doesn't know, did you want them here? Did you want them here? Did you want them here? Where you want them? And so it says, I don't know what to do that. Right? It's this dimension mismatch error. 2 and the 4 didn't match. Okay. One thing with matrices, an operation that it turns out, especially when we get to linear algebra, we'll often do, is flipping the rows and the columns. Yes?
When you were assigning the 4 different values, why did you not use commas?
Let's try that. Sorry, I'm trying to go back, but maybe I should. So here I use spaces. And so on the left-hand side, I had specified something that is 1 by 4. So if I want to be strict about making the left-hand side and the right-hand side match, I'd like to give Julia something that is 1 by 4. It turns out that if you give it commas, this is a list. It doesn't really have a specified number of rows and a specified number of columns. And so Julia goes like, oh, okay, I know what to do with that. That'll be okay. But suppose that we had tried the same thing, but now instead of separating it by commas, separating it by semicolons, what do you think would happen? So now on the left-hand side, we have something that is one row by 4 columns. And on the right-hand side, what do we have?
One column of different
Yeah, it's 4 rows of a single column. And so that, Julia still let us do it. So it's a little bit more forgiving than I remembered. But when you're trying to think about these things, try to keep in mind kind of like which dimensions match, right? You're trying to get things to match. Okay, so one operation that we often do is flip the rows and columns. That's going to become more important in linear algebra. And you guys already saw that this was this apostrophe operation. And that just, whatever was a row now becomes a column, and whatever was a column now becomes a row, right? So this 159 that was here in this first row now becomes the 159 on the first column. I don't think you're going to need that today, but it's just good to tell you guys about it several times so that when you do get to it, you'll remember it a little bit more. So what are typical things that we do with matrices? They're used for many, many, many things. Often, when you have a lot of data, you end up storing it in a matrix and doing something with it. And storing it that way. For example, suppose that you have multiple trials where you recorded something over the same amount of time, then that goes naturally into a matrix where, say, you have the different rows, might be the different trials, and the columns represent the different time points. And we already did that once for the memory voltages that we were plotting the other day. Actually, I don't know why I'm erasing the board, because I think I have this thing. Let's see if I can get this, do something on the screen. Another thing that we use matrices a lot for is if you're modeling neural networks. So for example, if you have a model of a network in which you have 4 inputs, and you're imagining that you might have a vector that we're going to call R. And so R would be one of these 4-element guys. And R1 is the first one, and R2 is the second one, and so on and so forth. And in many neural networks, artificial neural networks, and they're often used as models of real neural networks, you might think that you have multiple layers of neurons representing subsequent groups of neurons. And so you might imagine that these feed to the next layer. And a typical thing that is done in these models is that the input to this layer, the input to this neuron, say, might be a weighted sum of the activity over here. So what does a weighted sum mean? It means that each number that we have here, we multiply it by some weight, by some factor. So this one we multiply it by this one we multiply it by that one, this one we multiply it by that one, this one by that one, and so forth, to give us this output. So that would be represented by this sum. So this sum right here, the way I've labeled these, I've labeled this factor W11, this one W12, this one W13, this one W14. And the notation here, you'll see that there are 2 numbers that are going to end up corresponding to the rows and columns in the matrix. And the first number is the row, and is going to be who we're feeding to. So this is the strength of the connection from unit 1 to unit 1. This is the strength of the connection from unit 2 to unit 1, from unit 3 to unit 1, from unit 4 to unit 1. And the weighted sum is just this equation right here. Right? So these are all connections from units j to unit 1. You sum the activity of each unit j, of each rth unit j by its corresponding factor. You multiply it, and then you sum it all up. And let's say that that's the output of this unit. And you can imagine that you do exactly the same for the next unit. So you'd have another set of weights running onto O2, but this time the first index would be W2. And so on for all of the connections. And so what you end up, the way you represent the strength of the connections from all the units here to all the units here is through a matrix. And so in this matrix, again, the rows are going to be who the information is being fed to, and the columns are going to be who the information comes from. So it's from, to, from in the columns, and to in the rows. So that's a typical use of a matrix. And this multiplication right here is how we use matrix multiplication, and we'll be doing a lot of that in the linear algebra module that we're going to come to. But right now, I wanted to do a little bit more playing with matrices, and then I want to do our project for the day, plotting the flow field, which is something that we're going to do a lot of in the dynamics module, okay, looking at flow fields and dynamics. So before I do that, just one small in-class exercise that we're going to do, which is, let's suppose that somebody said, I want you to produce a matrix that has a certain number of rows and a certain number of columns, and I'm going to tell you, starting at which column, everything is going to be zeros, except for starting at a particular column for a certain number of columns, I want all those to be ones. Let's write a function that does that. This is another angle on something that's very much like 2D. How many of you have completed 2D at this point? Almost everybody. Okay. So 2D is the one that's graded. So I'm assuming that that's the one that is on people's minds. Okay, so let me take a vote. I was going to do this, this exercise as something that's like 2D, worth going through or not going through. Those that would like to see me do it, raise your hands. That's a substantial fraction of people. That's certainly more than 1%. Okay, so let's do it. Won't take that long. So here's what we want. We want the user to tell us the number of rows, the number of columns in the matrix. So say that it had been 3 by 4. And they're going to tell us a starting column and the number of columns that we want to be 1. So for example, if the starting column is 2 and n columns is 2, what we want is to produce a matrix that looks like this. So it's zeros everywhere, except for starting at column 2, and for 2 columns, where we want it to be 1. Let's write a function that does that. Let's call it column of 1s or something like that. And everything else that I'm going to do today is in the pre-written file. This one actually is not. So function column of 1s. And so we said, what are the parameters that we want for it? We want to know how many rows our matrix is going to have, how many columns it's going to have. We want to know where to start putting in the 1s, and we want to know how many columns of 1s we want. Okay. So let's call what we're going to return. Let's start building it. Let's call it ants. We're going to start by making a matrix, filling it with zeros, and then we're going to put the 1s in where we want. So to do that, we first use the command zeros just to build a matrix with that number of rows and that number of columns. And now what I want to do is access the columns that are indicated and set everything in there to 1s. So how could I do that? Any suggestions for what I should write here? I wish I could remember who raised their hands. I think you raised your hand, so I'm going to pick on you. Give me some suggestions to something to write. If you're not sure, you could say write zebra, and then I'll do something else. Any suggestions? Okay. So we want to access, say that we wanted to access this column. column number start, whatever that number is. So for example, if I wanted to access the second column, I'd write that. Right? If I want to access the column whose index is the number start, what would I write? Exactly, right? So when start has the value 2, that will access the second column. When start has the value 3, that will access the second column. So whatever the user of this function set as start, that's what we're going to be accessing. And now we want to set everything in there to the value 1. Yes?
Can you start call or are you saying start using?
Oh, start call. Thank you. Thank you. Yes, it should be the same name as whatever that is. So if I want to set everything in that column to 1, what could I write? Sorry, I'm still picking on you. Excellent. Okay. Now we wanted to do that not only for start column, but we wanted to do it for this many columns. So say that if the user had said, oh, n calls equals 3, we would have done it for this one, and this one. So we could write a for loop and loop over the things they told us. Sound reasonable? I suspect that you're just nodding to keep me happy, but that's fine too.
Would you not do like a start call colon 3, or like to, like if you want to do something to n, you colon n. Could you do something similar?
Okay, yes, so if we wanted to do it all the way to the end, we'd write exactly that, and then we'd be done. So I totally like where you're going. Now, they didn't say go all the way to the end. They said how many columns of ones they wanted. So what could we write there? Yeah.
Start column plus how many columns minus 1.
So you're suggesting we write something like this.
Yeah.
Okay.
No, the how
No?
many.
Oh,
instead of-
the how many, sorry, yes. Okay, and why minus 1?
To take out the starting point.
Yeah, so often when I'm writing something like this, I find it hard to kind of keep track of the indices. Should I put in a minus 1 or should I not? So just think of an example. Suppose somebody had said start call is 1 and how many is 1. So that means that I want just the first column. Right? So then we'd be asking, going from 1 to 1 plus 1, that's 2. No, we don't want both the first and the second column, so subtract the 1 so it's just the first column. Right? This, if start call is 1 and how many is 1, that would be the same as 1 to 1 plus 1 minus 1. Right? Let me put the parentheses so it's clear what happens. 1 plus 1 minus 1 is 1. 1 to 1 is, let me put it, make it more explicit. 1 to 1 is just the number 1. So in principle, this should do it. Whatever the user gives us for n rows and columns, start call, how many, we've built the thing that they wanted, and we return it. So let me save it. I type Alt-Enter to do the copy-paste into the read-eval print loop, the REPL. And now let's try and run it and see if it works. So let's say that we wanted 2 rows, 4 columns, and since I've been picking on you, now you get to choose where you want to start the ones and how many of them you want. We're starting at the second column, and how many columns of ones would you like? Say?
Just the second.
Just that one. Okay, so we want just 1. Yeah. Okay. So 2 gets mapped to n rows. The next one gets mapped to n columns. The next one gets mapped to start column. And how many columns? Just 1. Did it work? It works. What if we asked for 2 columns of ones? We get 2 columns of ones. What if we ask for 3 columns? Oh, 3 columns of ones. We get 3 columns of ones. What if we ask for 10 columns of ones? Well, it doesn't fit, and so we get an error. Okay, so small 2D-like exercise. Now let's do kind of like what I described as our little project for the day. And our little project for the day starts with a data file, which I need to remember, oh, I'm in the wrong directory. Hang on. Let me see where I am. Okay, this is more like it. And in the files that I sent out, there's a file called flowdata.jld. So let's load that. And this turns out to have two matrices, so let's access both. You can see there's a y and there's an x. So let's just pull them both out into local variables so they're a little easier to work with. And it turns out that they're both 17 by 17 matrices. So let me tell you guys a little bit of what they are. So that's what y looks like, and let me show you what x looks like. And so what they are is there's a grid of 17 by 17 points. We're looking at a grid of points, 17 by 17, not they're all 17 on the blackboard, of course. And that's the shape of these matrices. And at each of those points, the corresponding element of x is a position on x, y, on the xy plane, and the corresponding element of y is a position on the xy plane. So for example, x of 1, 1 is the horizontal position of a point, and y of 1, 1 is the vertical position of a point, and so that point is at this location. Those are its xy coordinates. So what we've gotten is 17 by 17 different point positions. And 17 by 17, we've got 289 different points laid out in a grid. And for each of those points, there's some function that somebody wrote. You guys don't have to look inside the function, where if you give that function a vector, a column vector, or rather just a length 2 vector that describes a point, it will tell you, if you tell it the xy position of something, it will tell you in which direction a particle that was at that position would move. Yes?
What does the include flow function mean?
Oh, the include is just like saying, read that file. So this is a file. Read it into here. So it's as if you had taken that file and just typed it line by line into here. And inside that file, I defined this function, and I'm telling you guys, if you want to go and look inside the function, it's a very simple function, so it might be very useful for you to look inside the function. Turns out you don't have to. In principle, it could be any function. Right? So it's just something that goes from position to, if you know the position, you know which way you're moving. And what we want to do is for each of our 17 points, we want to plot an arrow that tells us how it's moving. And that's going to give us a sense in this plane, given the motion, the dynamics defined by this function that some arbitrary person, in this case me, wrote, how would things move? So we want to end up by plotting a bunch of arrows on the screen. And the way these plots are typically made is that for any given point, for any position in the plane where a particle would move, you plot an arrow where the base of the arrow is at that position. The direction of the arrow tells you which way the particle would move, and the length of the arrow tells you how fast it's going. So for example, if we ask this function, flow function, a particle that is at position 1, 2, so horizontal position 1, vertical position 2, where is that going? That says, oh, this is its horizontal velocity, and this is its vertical velocity. Yes?
So wait, how do you know what parameters the flow function takes? Like,
Oh,
so you know that?
So I typed question mark flow function, and so that accesses the documentation for flow function. And I hoped that I wrote this descriptively enough that you could read that out from that. In principle, whenever you're writing documentation, you want to be able to answer that question for anybody that comes and looks at this thing. In this case, also, I'm just telling you what it does, but okay, so, and we can give flow function kind of, any point that we like. So we can do it 4, 5, whatever, et cetera, et cetera. So what we want to do is we want to take our matrix X, our matrix Y, and for each of the 289 points defined by those positions, find which way they would be moving, and plot a little arrow for that point. So that sounds kind of a little big. Why don't we break it down? So first, let's write a function that plots an arrow. And once we've written that, then we can worry about the rest of the things. We don't want to have to worry about everything all at once. And I'm trying to emphasize again, kind of like the reason why we gave you guys those little turtle graphics exercises, just to emphasize, build simple building blocks, and then from those you can build something more complex, try and separate your problem. Plotting an arrow, that's something that we can debug on its own. Then we're going to come back and worry about looping over positions and plotting lots of them. So for plotting an arrow, let's write a function that will do that. Let's call it, plot arrow. Or actually, let me put everything in a single file. I'm going to put it in this file, day 5. Okay. And what I'm doing now is already in that file pre-written day 5. So you don't have to copy anything. Okay. So let's write a function that will plot an arrow. In order to plot the arrow, what is it that we want to tell our function? We need to tell it where to plot it. We need to tell it where the base will go. And let's tell it how long the arrow is, and let's tell it what angle the arrow is making. So we could plot any arbitrary arrow. So we're going to want to tell it the x and y position of the base of the arrow, the length of the arrow, and the angle of the arrow. And if we're going to do that, the plotting that we're going to do is a little bit kind of like the turtle graphics that we talked about. What we want to find out is for an arrow shape, we're going to call plot, and we need to give it the list of horizontal positions or the list of vertical positions such that plot would end up making a line or a set of lines that looks like an arrow. So say you might want to plot an arrow that has these elements. So you could plot that, say, in 2 lines. You draw this, and then you need to raise your pen, and then draw that. I can't tell whether I'm going too slowly, too boringly, or too fast. But I can tell that I'm starting to lose you guys. Any questions at this point? Any questions about what we're trying to do or where we're going?
Let's just go back to when you made those arrays X and Y. When you made your X and Y arrays, I just missed it.
So I didn't make them. I loaded them from a file.
Okay.
So I'm telling you, somebody has come along and given you an arbitrary X array and an arbitrary Y array, and they've said they correspond to each other and they give you points X and Y. So that's why you missed it, because I just loaded them from the file. Yeah.
But the length of an arrow, is that just something you choose, or is that in file as well?
So that's going to come from this flow function. So for each point, we know what the horizontal velocity is and we know what the vertical velocity is. And so say, if we end up drawing this arrow, this will correspond to its horizontal velocity, and this will correspond to its vertical velocity. So flow function, for each position, the function flow function will tell us these things, and so that's enough information to figure out how long should the arrow be and where should it point. Yeah?
So are the points the velocity or the coordinates?
So the points in x and y, great question, thank you. The points in x and y are the positions, and flow function returns the velocities in horizontal, vertical coordinates. Did that answer your question?
And flow function just, like, how does it do
Some magical stuff. So why am I saying some magical stuff? Because the procedure that we're going to do is very general. for any flow function that we could write, we could write the program that we're about to write and plot the flow field for it. Okay. This particular flow function, since you're asking, let me show you what it is. So this particular flow function is extremely simple. It's just linear dynamics. It's a matrix multiplied times the position. But what I'm trying to emphasize is you guys don't need to know what goes in that, right? All you need to know is there's some little black box where if you tell it position, it gives you the velocities, and that's all you actually need to know in order to plot the flow field. And was there a question here?
But, sorry. The velocities are based on the position. So the velocities are based on the position, so they'll be unique for each.
Exactly. So flow function, when you call it, you tell it the position, and it says, at this position, flow function answers with, you gave me the position, I respond with the velocities.
And those
At
are
the
the
given
X and Y
position.
velocities, the two.
Exactly. This is the horizontal, the x velocity, and this is the vertical, the y velocity.
Wait, so those points that has nothing to do with the file that you loaded, the X and Y matrices?
Yeah,
They're just
totally different
points
thing.
in-
The x and y matrices were just positions in space.
Okay.
And then to turn those into motion, we needed an extra thing, which was flow function. And the program that we're going to write will work for any flow function. And that's why I didn't want to go into the details of flow function. But there's two steps. Positions, that's x and y, and then the velocities that we get from flow function.
The first output of the function is the X velocity and the second one is the Y velocity.
Exactly. First output is x velocity, second output is y velocity. Okay, I feel like we're more on at least roughly on the same page. So, for example, before we plot anything, say that we wanted to list all the points and all the x and y velocities. So let's make a temporary to this script in which we're going to do that. Okay, before we get into plotting. So we have an x matrix and we have a y matrix, and we'd like to go through all the points in both. How do we go through all the points in a matrix? Say it again. Okay, we could do a for loop. So here's my matrix X. Let's write a for loop for I equals, what would I write? Key thing that I haven't told you yet. If you want to ask how many elements a vector has, you use length, right? So you guys will remember if we had our vector vec, we could ask what's the length of vec, and it says it has 4 elements. Now if we work with matrices, a different command is this command size, or rather a different function. And that one returns number of columns, number of rows. So if we wanted to know the number of columns in X, we can do it like this. Right? It always goes rows first, columns second. So that means give me the second element that's returned. Or we could write something like this. And now n rows will have the value of the rows, and n columns will have the value of the columns, which in this case, they're square matrices, meaning they have the same number of rows and columns, so they're both 17. So if we wrote something like this, in fact, let me go explicitly over all the rows and all the columns. We could loop over all the rows. Now, we didn't just want to loop over all the rows. We wanted each and every individual point in X, right, in both X and Y. So what could we do now? If we want to cover, we've got a matrix, we've got a number of rows, we've got a number of columns, and we need to access each of these individually. So right now, we're looping over all the rows. Let's say that we also looped over all the columns. So then that would mean the first time we run, we'll be looking at the first row. And then in here in line 5, we'll look at each of the columns of row 1. The second time this outer for loop runs, we're going to look at the second row, and then we're going to look at all the columns of that second row, and so on and so forth. So we're going to end up looking at all the columns of all the rows. Does that make sense? Kind of? Yeah, more or less. So at this point, we could say our horizontal position and our vertical position and this loop would go over all the different points. Let's see if that works. Let me put a space here so it's a little clear. So we've looped over all the horizontal points. Each line, each time we're in here, we're looking at a point, and we're looking at its horizontal and vertical position. Now that we've got those, for each of those, we could ask, what velocity is there at that position? And how do we ask for the velocity given a position? In this case, we have this function, flow function, that goes from position to velocity. So we could say that the velocity, the horizontal and the vertical velocity, are going to be flow function of this vector. Let me call this just h and v for short, of h comma, oops, yeah, h comma v. So that will loop through all the points. Right? As we go through all the points, we'll find out the velocity for each of the points. And then what we'd like to do on top of that is plot an arrow for each of those. Does that kind of make sense? Yes?
This syntax of the Vx and Vy just separated by color, you go do that for tail arrays or like?
Actually, I'd forgotten, you can do that when the function returns two things. And I think I wrote flow functions in a way that it returns just one thing, so I think I'm making a mistake there. It turns out. So let's go back to the documentation to see what the heck it does. It says it returns a vector also of length 2. So actually, it will return one thing. And the first element of that, let's run it on something just to see what it does. Our flow function of 1, 2. Yes, it returns a single vector, not two things.
It's not like, because it knows that it's two elements, if you put a 2-element vector on one side, it will assign them?
No. When you write a function and you write something like this, then it returns them as two separate things. And technically, it returns them as a tuple of those two. And so you can pull them out. You can use them both as one thing and as two separate things, but it's not a vector, it's a tuple. If you want to get into those technicalities. For now, I would say, let's just return one thing, and it's returning a vector. We'll pull it out from the vector. So we've been able to go over all of the points that the files have, but we're not yet plotting anything. Right? We'd like to plot them in some decent way. So we'd like to plot the arrow. So let's make that function plot arrow. And for this function, we want to be able to plot an arrow at a given position, of a given length, and a given angle. So how are we going to do that? for an arrow that is at any given position, I'm going to remind you guys of some trigonometry from past experience. I know that some of you, this will be well known, and for some of you, this will be a refresher. Say that you have a line of length L, and you want to ask how long is this horizontal component and how long is this vertical component. The horizontal component is the cosine of the angle that the line makes with respect to the horizontal times L. This is, oh, I got this wrong. That's the sine. Sorry about that. No, we don't do that. This distance is L times the sine of the angle. And so that's how we can figure out from the length of an arrow and what angle it makes, kind of the horizontal and vertical positions of its points. And then the head of the arrow is the same again, but with an extra angle that here in this diagram I'm calling B. This thing is all recorded, so when I post the lecture, you guys can get this image and see how we went through all of this. So let's try and plot that out. So what we want is a line that goes from here to here. We're going to start with that. So we're being told the user of this function is giving us the starting position. So it's giving us the x and the y position of this point. And if the arrow is length L, what we want to be able to draw at least the first line of the arrow is what this point is going to be. So I'm going to try and simplify things a little to start with. Let's suppose that instead of drawing an arrow, we just drew a line. So it's length L. It's making an angle that we're calling ANGLE. This point is x comma y. This point over here, how do we figure out the coordinates of that point, given the diagram that I just went through? What is its horizontal position? So let me remind you, this distance is L times the cosine of the angle, and this distance is L times the sine of the angle. So if this is at position x, horizontal position x, vertical position y, what's the horizontal position of that point? So L sine of angle is this, so it tells us about the vertical displacement. And L cosine of angle is this, so it tells us about the horizontal displacement. So if this is at horizontal position x, at what position is this point? Say it. No, so this position is at horizontal position x, vertical position y. That's the x comma y that we're talking about here. And here I'm just asking, what's the horizontal position of this point?
X plus L cosine of the angle.
Right. So this one is at position x. We just want to move, wherever we were, move an extra L times cosine angle steps along. So everything along this line has a horizontal position x plus L cosine. And what's the y position of this? Y plus the sine of the angle. Okay. So now we know the 2 points of a line that we'd like to draw. So we can draw them. So when we plot something, it takes a list of x positions and a list of y positions. So the first x position is that. That's the base of the line. What's going to be the base of the arrow. And what's the next x position that we just figured out? So what's the x position of this point? The horizontal position. What's the horizontal position of this point? So if you move from here to here horizontally, if you want to move L cosine angle from x,
Oh,
yes, x plus len times the cosine of the angle, right? Because here's where we were. L times cosine of the angle is how far we want to go. So the new horizontal position is just the sum of where we were plus how far we want it to go. And how about for the y? What's the list of the y positions that we want to plot to do the line with?
Good question. Why do you have to go through all of this stuff if you already have the coordinates and velocity? Why don't we just add x plus the velocity is the final coordinate? X plus the x component of the velocity is the final coordinate, and y plus
We could do it that way. It turns out that I was getting ambitious and I wanted to plot the head of the arrow. And it's much easier to plot the head of the arrow if you're working in length and angle coordinates. For just plotting the base of the arrow, so if we wanted to plot this as well, we know this point and we know this point, but those are just quicker to figure out in terms of length and angle coordinates. So that's why I was doing it this way. If we're not going to plot the head, it's true that we could have skipped some steps.
the head of the arrow isn't an arbitrary shape.
We're defining it. This function is what's going to plot the arrows, so we can do whatever we like. I was thinking that it would be cute to draw a couple of lines like that at some angle that we define. I think we might end up only drawing the base of the arrow, in which case there would have been a simpler way to do it. It occurs to me that it's probably not a bad idea to go a little bit over this trigonometry because we're going to need it a lot later. So that's a warning. If you're looking at cosine and sine and you're kind of not remembering things, please go back to your textbooks and refresh your memories about that. Okay? We'll try to give you a refresher, but we can't really cover that stuff. So there's not enough time, so you're going to have to help us out with it. So the y position is exactly the same thing, except now we work with the sine of the angle. So now we've got a list of y positions. The same way as when we were plotting t comma v, we had a list of y positions, those were the voltages, versus a list of x positions, those were the t's. Now we've got a list of y positions, a list of x positions, and we can plot this semi-arrow that isn't too much of an arrow yet. Let's see if this works. Oh no, where am I? I've got it in the wrong directory. Okay. Okay, now got it. All right, so let's see whether we can plot this arrow-like object. So we want to plot it at some position. Let's say that it's at position 1, 2, and let's say that we want an arrow that's 3 long, and let's say that we want to work in angles, in degrees, instead of radians. So radians, as you go all around the circle, there's 2 pi of them, whereas degrees, there's 360 of them. So let's say that we want it at 45 degrees. 45 degrees, pi is 180 degrees, pi over 2 is 90 degrees, so pi over 4 is 45 degrees. So let's specify pi over 4. Let's see what we get on the screen. Okay, we got a line. Something that we can add to our plot command is this magic little command called aspect ratio equal. And what that makes is that horizontal units in x and y are going to be equivalent. So we don't get things stretched out horizontally or vertically. So now it really looks, even on the screen, like it's 45 degrees. So now that we've got that, we can try and go over all our points and plot the flow field for all of the points. So we've got our function plot arrow. We had our data. So this was from flow data. I'm just reloading the matrix so that the file that I'm writing will work on its own. And now we want to do what we've done before, which is loop through every single point, and for every single point, plot a line like this that will tell us about the flow field. So let's find the number of rows in X. Let's find the number of columns in X. And we'll just assume that X and Y are the same size. That turns out to be true. And then we're going to loop over all of them. That's what we had written before. And now, once again, we pull out what's the horizontal position of this point, what's the vertical position of this point, and now we use the flow function to find out what its velocity is. And now, because I wrote plot arrow in terms of angles, we have to refigure out what it is in terms of lengths and angles. Which I think for now, I'm going to let's do it. I think we're going to be able to plot the whole arrows, which is going to be nice. So the things that I'm trying to illustrate here in particular were with plot. I wanted to remind you guys as to how we could plot a list of horizontal positions and a list of the vertical positions, and then it joins all those points with a line. Here we're plotting just one line. If we get to plotting the head of the arrow, then there's going to be more line segments in that thing that we're plotting. And we're refreshing trigonometry, and here's a little bit more trigonometry refreshing. So flow function is going to tell us in its first element, in fact, we could run it like this. The first element is the horizontal position. The second element is the vertical position, sorry, the vertical velocity. And so we know that we want to draw an arrow that has these coordinates. But because I was stubborn and maybe stupid, I wanted to describe this arrow in terms of its length and in terms of this angle. So if I know the horizontal and the vertical positions, if I know this distance and I know this distance, what's the length? Somebody who's recalling Pythagoras' theorem from back in school. Square root. So the length is easy to figure out. If you guys remember that this squared plus that squared is equal to this squared, that's Pythagoras' theorem. And so you take the square root to find the length of the arrow. How about this angle? Yes. Yes, exactly. So the tangent of an angle is the same as if this were a unit length. What's this over this? So in this case, it's going to be the same as by over bx. So that means that if we use the inverse function, that's the arctangent. Let's just take the inverse, the arctangent of both sides. So this is let's say x over dy, so I can't read it, write it like that. The arctangent is the inverse of the tangent, so that means just sticking back. So the angle we can figure out the arctangent of the x. So now we've got something that we can plot. Right? So now we can call our function plot arrow. In fact, let me write it out explicitly. So length is going to be the square root of bx squared plus by squared. And the angle is going to be the arctangent of vy over vx. And now we can call plot arrow, because plot arrow took in x and y, and length and angle. And now we have x, the horizontal position, y, the vertical position, the length, and the angle. And so we can plot that for all of the points. Or at least that's our story. So let's see if that works. And one thing that is really easy to forget is that when you're running plotting commands in a script, in a file, at the end you want to tell the plotting system to show you everything it's done, and this is the show me command. Okay. So let's run that. And oh, where's the file flow data? Opening file flow data, no such file or directory. That's probably because it's called flowdata.jld. Let me see if, yeah, that's what it's called. Okay, so let's try again. And we're supposed to get this beautiful set of many lines representing the flow field. We didn't really get that. So what happened? Any guesses as to what happened?
Just kept overwriting the plot.
We kept overwriting the plot, because every time that we call plot, it replaces whatever was there before. So every time that we plotted a new line, it erased the old one. If you want to plot things on top of each other, you use this plot exclamation mark command. That's the one that says, don't erase the old thing, keep writing. So let's try again. And we can start with a plot nothing command that kind of clears the screen. And now let's try and plot all our things again. Okay, so now it's starting to look a little bit more interesting. I was hoping to get to a cute picture that related to dynamics, which is what we're going to be looking at in one of the later modules. And we're starting to approach that. So you can start to imagine that this describes a flow field that's kind of swirling around a point, right? So these lines tell you at any position, the length of the line tells you how fast you would be moving, and the direction of the line tells you in which direction you'd be moving. Right? So you can see that there's some kind of motion like this. Now we didn't plot the head of the arrows, so we don't yet know, if you're here, this one, does it mean that you're moving down and to the right or up and to the left? We haven't done that yet. Right? So it might be nice to do that. So let's try and do that. I think we're almost there. And then you guys can see the full flow field for this. So what are the things that we've been doing here? A couple of things when we're accessing matrices. Here I'm just trying to emphasize how you access the elements, looking at the rows and the columns. The thing before the comma is the rows. The thing after the comma is the columns. And that's how we can go through all the elements in the matrix. So this function plot arrow, we called it plot arrow, but we could have called it anything we wanted. Right? We could plot any shape we want. We could plot a symbol. We could plot whatever it is. Our program is now kind of independent of that. Right? It just takes a position, x, y, a length, an angle, and then we can do with it whatever we want. So let's make it plot an actual. And in particular, I would like is to plot an arrow that has an arrowhead that scales with the length of the arrow. We don't want to make the arrowhead always the same size, because say that we're plotting a tiny little arrow like that, we don't want the arrowhead to be bigger than the actual arrow. So how do we figure out what we want for that? I think we'll be just in time to do all of these things. So let's add some optional parameters where we define the length, the fractional length of the head. Let's call this FL, and we'll define this angle, I'll call it alpha, of what's the angle of this corresponding to the body of the arrow. And I'm going to make those optional parameters because maybe we want to play with them. I'm not really sure kind of what a good value for alpha is or what a good value for FL is. So we'll play with them a little bit. By making them optional parameters, that means once we've found the values that we like, we can just leave it like that, and the user doesn't need to specify them. So let's call this the fractional length. I don't know, maybe just starting at half the length of the arrow might be a good place to start. You guys have any preferences? A small arrowhead, a large arrowhead? Let's start with 0.5. And let's say that that angle alpha, let's make it 30 degrees to start. I'm going to write it in degrees. Okay.
Why do you have a semicolon?
Okay.
And then-
So the semicolon is the thing that divides the optional named arguments from the forced arguments. So I don't know if that's the right term, but the arguments that you need to call. So to call plot arrow, you need to specify 4 things. And then these others, you can specify them if you want, or if you don't want, you don't specify them. To specify them, you'd specify them by name. And here we're defining the name. Yes?
Do you need columns and semicolons for plot?
Oh, thank you very much. No, just one. Yes?
Wait, so fraction length and alpha are basically just constants for your function? Is that what you're saying?
We did this last time. Let's do it again. When you call this, fraction length is going to be a variable, just like x and y are variables inside your function. Fraction length is going to be a variable. And in fact, let me do an example right here. Let's say that we call it with x and this. So just a function that shows us what it has. And x, this, and that, once you're inside the function, they're variables, they have values, they're just like each other.
Okay.
So the difference between x and this and that is just in this line, in line number 1, when you're entering the function. And the way it works is that you can call the things after the semicolon are optional, and if you don't specify them, then they take on the values that you've written in that first line.
But you can change the values of.
But you can change the values, and let me show you how you do that. Ooh. Oh, abra 1, x is 1. This, what you write here in that first line, that's the default value. So if you don't specify it, that's the value that it will have. If you do specify it, you specify it through the name, and you give it a value like this when you call the function. And then inside, the variable this is going to have whatever value you pass here. And whichever ones you specify, those are the ones that take on the values from when you called. Whichever parameters you don't specify take on the default values.
I have one more question.
Go for it.
So if you're specify in like your comments or whatever what the variable's name is, you literally can't do anything.
Exactly. So when you're documenting something like this, so the typical documentation, did I just erase that? Yeah, I did just erase that. Or is it this one? No, here it is. So if you're writing documentation for something like this, actually for any function, kind of like the typical thing that you first do is just copy this first line into the documentation. Because then you're specifying the names for the user to see, and then you'd have a little sentence or something about each of these parameters. What is it? What does it do? Okay, so now I'm no longer sure that we're going to be able to do the arrow, but we're almost there. Maybe we will. Oh, one more question.
Do the sine and cosine functions accept both like degrees and radians?
No, so they expect things in radians. So we're going to have to turn it into degrees. So let's do exactly that. Let's take alpha, and here we specified it in degrees, and now let's turn it into radians. So we multiply it by pi, and we divide by 180, and now it's in radians. Okay, and let's at least plot this side of the head. So we went from here to here by adding L cosine, let's call this angle beta, L cosine beta, L cosine beta, and in the vertical position, L sine beta. Now, to go from here to here, we're going to do exactly the same thing, except now we're going to work with this angle on top of this angle beta. So let's just compute a new angle. Is going to be our original angle. So we're facing here. Now we're going to add 180 degrees. So with the original angle, we're facing this way. We add 180 degrees. We're now facing that way. And we subtract alpha. So now we're facing along this line. So it's going to plus 180 degrees in radians is pi minus alpha. So that's the new angle that we want to go. And so the next position is going to be x plus the length times the cosine of the angle. So namely, wherever we were before, now plus the length times the fractional length times the cosine of the new angle. So we're doing really exactly the same thing we've done before. So we went from x to this point, and now from this point, we're taking another step in exactly the same way we've done before, but now we're working with this new angle. And we're going to specify the y position as well. I think I'm just going to get there for that half arrow, unless I made a mistake, which of course is kind of likely. So now we're going and we add, right, that's the next step that we're taking. So now the line that we're plotting, if you look at the vector that we've written, we start here, up to another point, up to another point. So it's going to look, in principle, it's going to look something like that. Yes?
So you know, you spell fraction like the second line. Just the T.
Oh, thank you. Okay. So ideally what we do, we've changed plot arrow. The right thing to do is now go and debug plot arrow. We plot just one arrow, make sure that it's working. We're running out of time, so I'm just going to pray for the best, and I'm going to run the entire program and hope it works. Let's erase the screen, and I'm going to run it. And hey, you can now start to see little bits of arrows. Let me do that again on a slightly bigger screen. So now you can actually tell the difference between the base of the arrow and the head of the arrow. And you can see a little bit that the motion is kind of like, it's actually swirling inwards. And the same way that we plotted one side, we could have plotted the other side of the arrow. In the file that I sent out, plot arrow plots the full arrow, and you can see the full plot.
Just a general question.
Yeah.
Does Julia care about white space?
Does Julia?
About white space in code?
In general, no. Okay, that's it for today. If you're one of the few people that haven't finished 2D, you have 2 more labs in which to ask for a lot of help.